Welcome to this video where we will be talking about errors of our numerical solutions for ODEs. So by the end of this video, you will be able to determine the order of the numerical ODE solution method. Well, why do we have to talk about errors? Well, we know that if we don't find an analytical exact solution, but instead find a numerical solution, we will always make errors in our numerical answer. And here we're going to focus only on errors that are due to truncation. But we know that we will also have a round-off errors, but we will not specifically look at these here, right? Even though they will be, of course, present in our numerical solution. So let's look at, as an example, Euler's explicit method. Euler's explicit method was the new solution yi plus 1 is equal to the old solution yi plus the right-hand side of the ODE evaluated at the known solution xi yi times the step size of h. Now, in order to calculate the true error, we need the true solution. But we usually don't know the true solution because if we did, what's the point of calculating a numerical solution in the first place? So let's instead use again the trick that we've used previously that involves the Taylor series. So let me write my true solution as my solution at the point I plus a step size h times the first derivative at the point xi plus, in a Taylor series expansion, 1/2 h squared times the second derivative at the grid point xi, and so on. And now these infinitely many terms will be combined using Taylor's theorem to the term 1/2 h squared times the second derivative, not evaluated at xi, but at some unknown location between xi and xi plus 1. That's Taylor's theorem. So I'm just expressing the true solution by this Taylor series. Now I can't use this really to find out what my true solution is because I don't know the value of xi I. But let me use the ODE, right? So if I use the ODE, I know that, well, the first part remains unchanged. yi plus 1 true solution is equal to yi plus h. And now I'm going to use the ODE for dy dx. And that says, well, that has to be f at where I calculate this derivative, and that's at xi yi. So I have to evaluate the right-hand side function f at xi yi plus 1/2 times h squared times, well, this second derivative, which is simply the first derivative of the right-hand side, but evaluated at an unknown location xi I and the corresponding y value at that xi I. Okay, now if we do express the true solution like this, then we can calculate the true error. It's only based on the truncation error as a reminder. So the true error E would be equal to the true solution minus my numerical solution. The true solution I've just expressed using the Taylor series, so I'm just going to copy-paste this term into the equation. And I'm going to subtract from it my numerical solution that I will determine using Euler's explicit method as an example. So I'm going to subtract the numerical solution, which was yi plus f of xi yi times h. I'm going to subtract that from the true solution. Okay, so let's see what we have. We have yi minus yi, that drops out. I have h times f at xi yi minus h times f at xi yi, that drops out as well. And so therefore my error is simply 1/2 h squared times f prime, the first derivative of the right-hand side of the ODE, evaluated at an unknown location xi I and y at xi I. Now, what is important about this? Well, the important thing is that this error is proportional to the step size squared, which means that this truncation error is order h squared. It's a second order truncation error. But truth be told, this is the error only if we start our Taylor series at yi, with yi being a true solution. So if we start from a true solution, then I know that if I do forward Euler from a true solution, I will get an error, a truncation error, that is proportional to the step size squared. And we'll call this the local truncation error. It's the error that we do by doing a single step starting from a true solution. Now, the total truncation error, also called the global truncation error, at our point I plus 1, however, is the sum of all the local truncation errors up to that step I plus 1, right? Because my solution at xi, yi will not be the true solution because I've obtained it using forward Euler, and thereby I have made a truncation error to reach yi, and it can't be my true solution. Now, how many steps did we have to take to reach the point I plus 1? Well, the number of steps is the x location at I plus 1 minus my start location from the initial constraint, x1, divided by the step size, h. And this kind of assumes that we do a constant step size h from one point to the next. Now that means then that my error is equal to, well, a half times h squared, but now times the sum of all of these f primes from all the prior steps. So from I equal to 1 to n sub I plus 1. So that's a half h squared times. Now what is this? Well, I'm summing up different f prime values over all these separate intervals. So let me call this an average value of f prime, right? And it's an average value if I divide this by the number of terms that I sum up. So if my average is the sum divided by ni plus 1, in order to get the sum, I have to multiply it by ni plus 1. Okay, so that's a half h squared times, well, ni plus 1 was the distance from xi plus 1 to x1 divided by the step size h. So let me substitute this in. Times this average value of f prime. Now what do I have? Well, I have an h squared that I now have to divide by h, which means that this term, right, leaves me with h to the power 1. So the error, the global truncation error, is actually proportional to h, and therefore this would be a first order method globally. So here's a summary of the solution techniques for ODEs, first order ODEs, that we have covered so far, with their local error and the global error. We've had the explicit or forward Euler method, which is second order locally, first order globally, that we just saw. We can do the same analysis for the backward Euler or implicit Euler method, and that method is locally second order, globally first order as well. Now the modified Euler method, on the other hand, is locally third order. So that means if I do one single step from an known analytical exact solution, I will make a third order error in the truncation error. But if I step from a known solution to a solution through multiple steps, I will have made a global error that is second order. And then the midpoint Euler method is locally third order as well, and the global error is second order. Now, when we talk about the truncation error or the order of a method, what we refer to is always the global error. So these methods are characterized by their global error. So the midpoint and modified Euler method are second order. The two explicit and implicit Euler methods are first order. Now, why are some methods higher order than others? Well, the first order methods, if we look at them, they use the slope from either end of the interval from xi to xi plus 1 only. It's either f using only xi, yi, or using only xi plus 1, yi plus 1, as is the case for the backward Euler method. Whereas these second order methods, they use either an average slope or a slope from somewhere within the interval. So the modified Euler method uses an average slope at the two endpoints. The midpoint Euler method uses a slope from within the interval from xi to xi plus 1 at the midpoint. So why don't we try to push this idea to get to higher order methods? Let's use averages of slopes calculated at multiple intermediate points. And that's exactly the idea that's behind Runge-Kutta methods that we will talk about in one of the following videos. Thank you for watching.